All right, here's your video key for problem set 2.4. Number 1, find the average rate of change. Remember, average rate of change just means slope between 2 points. So we need to find the y value at 1 and the y value at 3. The common mistake here is looking at this interval 1 to 3. People want to find the y value at 2, but remember this is really just the slope of a secant line. A secant line is a line between 2 points. So on the graph of x cubed minus x, whatever that looks like, we're just finding the slope of the line that connects the points at x equals 1 and x equals 3. So f of 1, which will be the y value at 1, is 0. F of 3, which is the y value at 3, is 24. So this is 24 minus 0 over 3 minus 1, which is 12. Average rate of change, slope between 2 points. Okay, part A on number 3. Number 2 just defines the secant line, which I already said for you. Average rate of change again. So same question as before. So you do 340 minus 150. It's just slope between these 2 points over 45 minus 23, which comes out to approximately 8.64 flies per day. Really, you should round to 3 decimal places. I only have the 2 decimal place answer for some reason. Round everything to 3 decimal places, though, because that's what they do on the AP exam. How does this relate to the secant line through the 2 points? It's the slope. But then part C says, what if we want to know how fast the population was growing on day 23 itself? So this is the idea of slope at a single point on day 23 itself. And so we want the slope between point 23, t equals 23, and t equals something really close to 23. So this is where we draw a tangent line. See how well I can draw a tangent line on this app. Oh, not very good. Try that one more time. If it lets me undo it, there we go. So we'll draw it from here to here. It doesn't. I don't know how to draw straight lines on here. If I can, I don't know how. If I can't, then that's probably why I don't know how. But in any case, a tangent line. Remember, at places close to the point of tangency, like right here, your tangent line needs to look just like the curve. So I'm trying to make the green line look like the blue. And then, if the green line looks like the blue, then the green line is a good representation of the slope at the point at the point 23. 23, 150, but really we just need the x value. So at 23, the slope of my green line is really close to the slope of the blue line. Therefore, it's a good estimate for the slope of, or the slope at 23 itself. So you just find 2 points on the line you drew. Remember, a line has a constant slope, so any 2 points you use, you should end up with the same slope. The points I used were, it doesn't really matter here what points you use. On my handwritten key, I used 1550 and 3300. You can look at the handwritten key for a nicer version of like the tangent line and stuff like that. All right, now here is the algebraic way to do the same thing. So we're going to find slope at a point, which we've done before. We just actually called it speed at an instant. But really, if you have a position versus time graph, then the slope is, it's actually your velocity, but we'll talk about those differences as time goes on. So here we're just using 2 points, 3, 9, and then something slightly bigger than 3. Remember, our function here is x squared. So that's where the point 39 comes from. And then 3 plus h is slightly bigger than 3. And then we do plug 3 plus h into x squared and get 3 plus h squared. So this is our, and for some of us, I would suggest actually writing it out like this. This is like your x1, or sorry, I'm going to call this x2, y2. That's a terrible 2. Both of those are terrible 2s. And this is our x1, y1. So I'm going to do, just setting up the formula for slope, 3 plus h squared y2 minus y1 over x2, I'll put that in parentheses just to distinguish it, you don't really need it, minus x1. So anytime you're doing a problem like this, your denominator is always going to end up being just h, because you always have a number plus h minus that number. And now we just simplify this bad boy, and the numerator is 9 plus 6h plus h squared minus 9 over h, which gives us just 6h plus h squared over h, which is just 6 plus h when you simplify that, which goes to 6 as h goes to 0, or when h is a really, really small number. And so our final answer is 6. Well, sorry, that's actually just our slope. Now here the question actually says, write an equation for the tangent line passing through the point. So we want an equation for the line that passes through this point, and so you need a slope and a point. Well, we have our slope, we just found it, it's 6. And the point it passes through is the point of tangency, which is the point 39. So now we can just use point slope, and our final answer is actually y minus 9 equals 6 times x minus 3. And so that is the equation for the tangent line that passes through the point 39. Or the equation for the tangent line at the point 39, I should say. All right, number 5 is just the mathy way to write exactly the process we just did on number 4. This is y2 minus y1 over x2 minus x1, which I said already will always simplify down to h. So number 6 is the same question. We just are doing this in the abstract, which means we don't have actual numbers. It says find the slope of the curve at x equals a. So the points are a1 over a, and then something slightly bigger than a, so a plus h, and then f of 1 plus h, which is 1 over a plus h. F of a plus h, I'm not sure what I said there. Okay, so now we have our y2, 1 over a plus h minus y1 all over x2 minus x1, which we know is going to be h. Now remember, we're actually doing the limit of this as h goes to 0. So really I should write this every single time, although I typically don't, but just know that you're finding a limit. Okay, this is a complex fraction, so typical strategy is get a common denominator on top. So this is equal to a over a times a plus h minus a plus h over a times a plus h all over h. Be careful with distributing your negative sign here in the numerator. So this negative sign, where's my pointer? This negative sign right here needs to be minus a minus h in the end. So be careful with that. I see a lot of mistakes over time with that algebra. So this becomes a, so the a's cancel and you're just left with negative h over our common denominator, but then it's double division. So it's negative h over ah times a plus h. And then these h's cancel, leaving us with negative 1 over a times a plus h. Again, don't lose sight of the fact you're doing a limit as h goes to 0. And so, like all limits, we try to do some sort of algebra, make whatever h or x is approaching plug-inable. Since that h that was a factor on the bottom just canceled, now I can plug in 0 for h, and I get negative 1 over a squared. And so this is the slope of 1 over x in the abstract, where a represents any x value. So now I can say, hey, what's the slope at x equals 3? And you just plug 3 in for a, and you get negative 1/9. What's the slope at x equals 5? Negative 1/25. And so finding it in the abstract allows you to find the slope quickly at any given point, rather than going through that process of that we just did like on number 4 for different points. You can do it in the abstract and then find the slope at any point quickly. Part B says, where does the slope equal negative 1/4? Well, the slope is negative 1 over a squared. That is a representation of the slope. And we want to know when that equals negative 1/4. Well, that's the same thing as saying when does a squared equal 4? So it's at a equals plus or minus 2. Okay. Part C, what happens to the slope of the tangent to the curve at the point a1 over a? So we're looking at the slope of the tangent as a approaches 0. So remember, our slope of the tangent is negative 1 over a squared, if I can get this to right. So that is the slope of the tangent line. So as a goes to 0, that means our denominator gets really, really small, but positive, and 1 over a small positive is 1 over really small is really big, but we have that negative in front. So it's going to go to negative infinity. That just means the function gets steeper and steeper and steeper as you approach 0. And if you think of what the graph 1 over x looks like, that should make sense to you. As we approach 0, what happens to the slope of this curve? Like right here, well, that's a negative slope and it's really steep. This is also a negative slope that's really steep. And so it's consistent with things you already know about the graph. What happens to the slope of the tangent as a moves away from 0? So as a goes to infinity. Well, as a goes to infinity, we're talking really about negative 1 over a squared as a goes to infinity. And that's 1 over a really big number, which is really small. Again, that's consistent with the graph. If you look right here, as we go this way, the slope approaches a slope of 0 because we have a horizontal asymptote there. And then the last part of this question, think about the graph. Are your previous two answers consistent with the graph? Well, yes, that's what I just discussed. All right. So now we're just giving a name to this thing. This is the thing we found the limit of already. It's called a difference quotient. And then it says if we interpret this as an average rate of change, the limit is the function's rate of change with respect to x at x equals a. That's just saying you're finding the slope at a point. So B says explain this in your own words. Slope. You're finding slope, you're just finding it at a single point. All right, so a normal line is just a line perpendicular to a tangent line. So AA says write an equation for the normal to the curve. So if we find the slope of the tangent line at x equals 1, which is doing that whole limit as h goes to 0 thing, and then we do the opposite reciprocal, and then we do point slope. We know what point it's going to pass through because it's at x equals 1, and we can find the y value just by plugging in 1. So when x is 1, so we have x equals 1, y equals 3, just from plugging 1 in. And then our points, our coordinates here, at x equals 1, so we have 1, 3, and then we have 1 plus h. For our x2, and then f of 1 plus h, which is 4 minus 1 plus h squared. So that's our y2. Okay, so setting up what's called the difference quotient, but again, just slope between 2 points. 4 minus 1 plus h squared, that's y2, minus 3, y1, over x2 minus x1, which we know is just going to be h. And we're doing the limit of this as h goes to 0. We simplify this. So just to save you some time, this is going to end up being, and you can look at the handwritten key for more details here, but you get negative 2h minus h squared over h once you simplify that, which is exactly equal to the limit as h goes to 0 of negative 2 minus h, which as h goes to 0 gets us negative 2. So the slope of the tangent line of f of x equals 4 minus x squared at x equals 1 is negative 2. So the slope of the normal line then is 1/2, and the normal line passes through the same point as the tangent line. So the point is still 1, 3. So then we just do y minus y1 equals our slope. Remember, it's perpendicular, so it's opposite reciprocal times x minus x1. And that is the equation for the normal line that passes through, or the normal line at x equals 1. Okay, referring back to problem set 2.1, we know that y equals 16t squared was the vertical distance traveled of a falling object. A body's average speed along a coordinate axis for a given period of time is the average rate of change of its position, y equals f of t. So that's what we talked about before. I was just finding the slope between 2 points. But its instantaneous speed at any time t is the instantaneous rate of change of position with respect to time t. Write this as a limit. All this is saying is, hey, slope at a point, if you're looking at a position curve, is the instantaneous speed. It's like how fast that object is moving at that moment. So to write this as a limit is exactly what we've been doing with this thing called the difference quotient. And you just do the limit as h goes to 0 of, and then we're finding it at t. So it's f of t plus h instead of like a plus h. We're using time. So minus f of t. So that's, again, just y2 minus y1 all over h, like before. And then c is going to go through that same process, finding the slope at a point, but that's going to tell us the speed at t equals 1 second, using 16t squared as our function. So we're doing the limit as h goes to 0 of 16. Our final time will be 1 plus h, so 16 times 1 plus h squared, minus 16 times 1 squared, which is 16, all over h. So I'll save you some time simplifying this, but just multiply out the numerator. Your 16s will cancel, and then the h on the bottom will cancel if you do your algebra correctly. And so you end up with the limit as h goes to 0 of 32 plus 16h, which as h goes to 0 is just, that's a 16. See if I can make that look a little nicer. Apparently not. Come on, right. All right, whatever, 16, so 32 plus 16h. And that limit as h goes to 0 is just 32. Units are provided in the question, so I'm going to provide units in my answer, 32 feet per second. And there you have it.